We're looking at the snap-on version of the power probe. It's a EECT900 multi-probe ultra circuit tester. And I want to point out a couple of things I've noticed about this tool. First of all, when you turn it on, it opens to the screen that says switch, and you have to select how you want the switch set up. I have it set up to latch just so it's easier, but you can change it to pulse 0.5, and then over here you can change how many seconds it pulses, or you could change it to momentary. I'm just putting it on latch for ease of use. So once it's there, you select M, and then I want to scroll up and show the ohms reading for a minute. I was fascinated by this, and I don't like ohms. I don't think it's a very good tool for diagnostic personally. But let's just sit on the ohms screen for a minute, select M, and notice I have 0.6 ohms. Now I have 0.3. I have to put the probe to ground. And currently I have the end of the power probe, so you can see here, hooked up to this wire for this water pump. It's just a SureFlow RV style pump is what I'm using for my load. So I put that on there, and you'll notice I have 0.5 ohms of resistance, 0.6. Okay, so now I want to actually power this pump with the probe. So I've noticed that if I move my menu screen to amps, when I'm on amps, it also tells me the ohms. This thing, it's like about a 14 amp start, but it doesn't exceed like 3 amps or something. So I put it on 5, and it typically will roll it. So I have a current clamp wrapped around this thing, and I have the current clamp hooked to my scope meter. We'll get back to that in a moment. So remember, it was 0.6 amps earlier. So let's power this thing on. I hit the button on the top. The pump's going. 6.4 ohms it says for resistance, and 1.9 amps at the tip. But I want to show you that when it first started up, it took 14 amps to get it to roll, and then up here to, let's move the cursor up, this cursor, move it up here, about 2 amps. Yeah, that's about right, 1.7 amps. This isn't perfectly scientific, but let's zoom in on it a little bit. So let me unhold this screen. Let's move this zoom in a little bit so we can see it. Let's change our time base so we can stretch it out a little bit and make sense of it. Let's hold on to that. That's what a motor waveform looks like when you're looking at current. So let's hold that screen right there, okay? I'm going to turn this off. Let's move our cursors down. Now an average amp draw, obviously we're getting the highs and lows of the motor going around. But let's just hit it right about in the middle. And then the other cursor needs moved up a bit here. So right about there. Considering my current clamp was calibrated to my scope meter, which I did calibrate it and it was darn close. I got about 1.82 amps of draw on my current clamp. And over here, pretty darn close, 1.82, somewhere in there, with 7.2 ohms of resistance. So let's come back over here now. Let's unhold this screen. Let's zoom back out of this a bit. That's what I'm looking for. Let's get the time base back to where I had it. And let's cycle this on and off. Wow, look at that. So we all know that the startup current of a motor is higher than the running current, I hope. But what I find fascinating is the current here is 1.6, and it shows based on the current and the voltage that we have a resistance reading of 7.5. So it's actually giving you the true resistance based on the voltage and the amperage. I think most of us know that for diagnostic purposes, resistance can be useful, but in a circuit that's not functioning, it's fairly irrelevant because we haven't considered current flow, temperature coefficient, and if we just measure the resistance of this motor and do some math, it's going to look like it has a huge current draw, which it does at startup, but then you have to consider other factors for running current. So it's my little Ohms is a liar discovery with the current on the power probe. And the power probe does a pretty good job of showing it in real life. That's my side discovery. I hope that helps.